Hello everyone, I am Kotaro Fujimura from the University of Osaka. We introduce a novel lighting system combining an LED display and an aperiodic lens array. Projection mapping is a technology that projects images onto physical objects to alter their visual properties. However, its practical use has a strong limitation. It requires a dark environment. As shown on the left, if we perform projection mapping in a dark room, we can achieve high-quality projection. But if we perform it in a bright environment, as shown on the right, the environmental lighting heavily washes out the dark components of the projected image. Consequently, the contrast drops significantly. To maintain projection quality, we are forced to darken the entire room. We call this the darkroom constraint. This darkroom constraint causes two major problems in augmented reality experiences. The first problem is the loss of environmental awareness. In a dark room, users cannot easily see surrounding objects or other people. This ruins one of the greatest advantages of projection mapping, the ability for multiple people to share an AR experience together. The second problem is the breakdown of optical consistency. For example, to realistically represent a specular material like metal, the surrounding environment must be reflected on the object's surface. However, in a dark room, there is no environment to be reflected. As a result, the projected object looks very unnatural. To solve this problem, a method called target-excluding lighting has been studied. As shown on the left, this method replaces typical room lights with multiple projectors. It selectively illuminates the surrounding environment while avoiding the projection target. This approach successfully achieves both a bright environment and high-contrast projection mapping. However, to realize target-excluding lighting with practical and natural illumination effects, we believe that the lighting system must satisfy the 5 key requirements shown in this table. The multi-projector method has a wide luminous distribution and high spatial controllability. However, since a projector approximates a point light source, its effective light source area is small, resulting in unnatural hard shadows cast by occluders. Furthermore, installing multiple projectors increases system scale and complexity. To overcome these issues, we propose a novel target-excluding lighting system. In this research, we adopt light field illumination, combining an LED display with a lens array. In this setup, a phenomenon called crosstalk occurs. Crosstalk means that light emitted from a single LED pixel passes through multiple lenses. This allows us to achieve a large effective light source area and a wide luminous distribution within a compact form factor. However, if we use a conventional periodic lens array, unintended dark spots appear in the non-projection target area during target-excluding lighting. In other words, the spatial controllability becomes low. This happens because the effect of the turned-off LEDs periodically overlaps due to the lens periodicity and crosstalk. To solve this artifact problem, we propose an optimization method that arranges the lenses aperiodically. Although the luminous efficiency decreases slightly, the spatial controllability is highly improved. The advantages of this configuration, such as a large light source area and compactness, are maintained. The key technical components of our research are this aperiodic lens optimization and 3 computation methods for LED luminance patterns. First, I will explain the optimization method for the lens arrangement. We adopt a greedy algorithm that places lenses one by one. In the first step, we calculate candidate points for a new lens. Next, for each candidate, we calculate the crosstalk distribution. Specifically, we first identify the LED pixels that illuminate the projection target. Then, we compute the distribution of the crosstalk images formed by these LEDs. After that, we evaluate the uniformity of this distribution using 2 metrics, dmin and QVMR. dmin represents local uniformity, evaluating the nearest neighbor distance between images to ensure they are not too close to each other. QVMR represents global uniformity, evaluating the overall bias by dividing the evaluation plane into regions and calculating the variance to mean ratio of the number of crosstalk images. Finally, we select the candidate point that maximizes the evaluation function, E, and place the next lens there. This process is repeated until no more lenses can be physically placed. This slide visualizes the optimization results. The search map on the top right shows the evaluation values of all candidate points at a certain step. As shown in the bottom right, with a periodic array, the crosstalk images overlap periodically. However, with our proposed aperiodic arrangement, the crosstalk images are effectively dispersed. Next, I will introduce our three computation methods for LED patterns. The first is the light transport matrix, or LTM-based method. This method vectorizes the camera image captured when each single LED pixel is illuminated and aggregates these vectors into a single matrix. Then, we compute the optimal LED pattern by multiplying the inverse of this matrix by a desired target mask camera image. This method perfectly accounts for global illumination. However, its main limitation is that it requires time-consuming recalibration every time the scene changes. The second is the optical ray tracing method. This method utilizes Helmholtz reciprocity. First, we project white light onto the target and capture its reflection on the LED surface. Based on optical reciprocity, the LEDs that appear bright are the ones illuminating the target. We simply turn those LEDs off. This allows for single-shot calibration and supports specular reflections like mirrors. However, it cannot handle complex global illumination, such as interreflections. The third is the geometry-based method. This method ignores global illumination and considers only direct illumination. We acquire the 3D coordinates of markers on the target using a motion tracker. Then, we trace virtual rays to the LED surface and compute their convex hull to define the unlit area. Because the computation is extremely fast, it runs in real time. Therefore, it enables dynamic target-excluding lighting for moving objects. Here is our experimental system. It consists of an LED display as the light source and the optimized aperiodic lens array. It also includes a projector for projection mapping, 2 cameras for calibration, and multiple motion trackers. Now, let's move on to the experimental results. First, we verified the effect of the lens optimization. The left image shows the result with a periodic lens array, and the right shows our aperiodic lens array. As you can see in the luminance profiles below, the periodic lens array generates unintended dark spots. In contrast, our proposed method successfully suppresses them, achieving uniform illumination. Next, we quantitatively evaluated the contrast of the projection mapping. The dark room environment, shown on the far left, has the highest contrast of 0.294. All three of our proposed computation methods achieved contrast values of 0.2 of 4 or higher. This means they maintained over 80% of the darkroom contrast. Compared to the typical bright environment with a contrast of 0.148, you can see that our system significantly improves the projection contrast. However, differences between the methods appear when we place a mirror in the scene. The geometry-based method ignores global illumination. Therefore, the target is illuminated by the reflection from the mirror, reducing the contrast. On the other hand, the LTM-based and optical ray tracing methods correctly turn off the LEDs, considering the mirror's reflection path. As a result, they maintain high contrast even with reflective objects in the scene. We also projected specular material content to confirm optical consistency. Our target-excluding lighting makes the surrounding environment visible while preserving the high-contrast specular reflections on the target. This confirms that our system successfully maintains optical consistency and visual realism. Finally, here is the result of dynamic projection mapping. Please take a look at the video. First, this is the typical bright environment where all LEDs are turned on. The projection mapping is applied, but the contrast is very low. Now, the system switches to target-excluding lighting using the real-time geometry-based method. Only the target object is strictly kept in the dark, while the surrounding environment remains brightly lit. Finally, we apply the projection mapping onto the moving target under our target-excluding lighting. Even in a dynamic scene, our system successfully maintains high contrast and natural environmental lighting. Here is a summary of this presentation. We proposed a novel target-excluding lighting system using an LED display and an aperiodic lens array, which enables high-contrast projection mapping. As our future direction, the proposed approach has several technical limitations. One of them is the reduced light throughput due to sparse aperiodic packing using a single lens type. Thank you for your attention.